Assalamu alaikum guys. Today we are going to start another new chapter, that is the ionization energy. Actually, we have studied about this ionization energy in our earlier subject. So now I am going to speak about what is meant by the ionization energy, how it shows the variation of the periodic trends according to that down the period and the down the group on your S block and the P block elements. So I am Najmunisha Ashaf. I came to explain you about the major impact of the ionization energy and the atomic structure. Let's we move on to the chapter. So before we start the subject, whatever to study, first we will go through the content, what we are going to study now. First thing is the introduction. Under introduction, I'm going to speak about what is meant by ionization energy. Yes, we have already studied, right? Here I'm going to introduce what is called the first ionization energy. The symbol is I1. And the second thing is the second ionization energy. The symbol is I2. The first ionization energy and second ionization energy further you can understand once I explain the definition. This is what we are going to speak here. And next one, the periodic trends in the first ionization energies. So this is what we are going to speak here. The trends we are speaking only for the first ionization energies, right? So according to that, you should be able to find the trends in the first ionization energy in the periodic table, so that you can find along the period, down the group. According to that, you should be able to explain what is the periodic trend of the ionization energy. The first ionization energy, right? And next, the variation of the first ionization energy with atomic number of elements. Yes, the first ionization energy is showing a impact on the according to their atomic number of elements. Therefore, according to your atomic number of the elements, the ionization energy also varies. Right. This is what I'm going to speak here. And the final one is the variation of the first ionization energies along the first and second period. Okay. So earlier one I have spoke about what the atomic number of elements, and this is what just commonly the periods, the first and second period. Let's we move on to the introduction and keep on the definitions, and we'll understand what is meant by the ionization energy one by one. So can you recall what is called the ionization energy? Yes. The ionization energy of an atom or ion is the minimum energy required to remove an electron from the ground state of isolated gaseous atom or ion. Simply you can say the minimum energy needed to the minimum energy required to remove an electron from your ground state or isolated ion or atom, which is the loosely bound electron we are talking about that, right? That is what the minimum energy is calling what the ionization energy. So we already know what is meant by the ionization energy. And what is called for the first ionization energy? I1. In this, the first ionization energy is the energy needed to remove the most loosely bound electron from a neutral gaseous atom. This is very important, guys. The ionization energy, we are talking about what? You have to remove an electron from your ground state of the isolated gaseous atom or ion. First ionization energy always what? It's energy needed to remove the most loosely bound electron from a neutral gaseous atom, not atom or ion. So example. The first ionization energy for the lithium atom is the energy required to the process. So what is happening here? So when you take the lithium, yes, Lithium is becoming gaseous, always under gaseous state, and it's becoming as what? Lithium plus. And ionization equation is you have to equal the charges, and that is also gaseous. Right. So this is what we are called the energy needed for this process, that we are called what? The first ionization energy of lithium. Simply we can say, right? The lithium gas becoming as lithium plus gas with the electron. And what is called for the second ionization? First ionization energy resembles what? The minimum amount of the energy needed to remove an electron, which is a loosely bound electron from the gaseous atom. That is the first ionization. And what is called for the second ionization energy? It's the energy needed, the minimum amount of the energy needed to remove the second loosely bound. That is first loosely bound electron. This is what the second loosely bound electron of an atom from the gaseous monovalent cation. Earlier one always should be neutral atom. Now we are going to step into the second ionization energy. It will happen after first ionization energy. Therefore, it is what the second loosely bound electron of an atom from the gaseous monovalent cation to form a gaseous divalent cation. So forth. For the successive removal of additional electrons. Thus, the second ionization energy for the lithium atom is energy associated with the process. So how they have done is, let's redo. So earlier one, the lithium, right? The first ionization energy at the gaseous state. Okay. This is what you can say I1, right? Formation of lithium gas, lithium plus gas. Now, from the lithium gas, I am going to prepare from lithium monovalent cation. I am going to prepare divalent cation. Yeah. And this is, you can say what? I2. Second ionization. You can say about this. This is the way. The lithium gas, from the lithium gas, the neutral atom, you have formed the monovalent cation, that is first ionization energy. And from the monovalent cation, if you want to prepare the divalent cation, the energy needed for that process is called the second ionization energy. This is what is the definition for this. Right? So the ionization energy for given element increase as the successive electrons are. So always the I1 is less than the I2, I2 less than I3, I3 less than I4. That is the increasing order. Always the ionization energies are increased for the given element as it is the successive electron order. And now you should be able to understand this trend. The trend is because why this is increasing as the ionization increasing with your Successive electron remove. So the successive electron removing being pulled away from an increasingly, therefore you can make more positive ion requiring energy also will be increased. So this is what. Why this spread? Why I1 is? What is the reason for having this spread? So I1, I2 and I3. What is the reason of this increasing? We said the successive removal of electron. Yes, the trend is because the E successive removal and electrons being pulled away from increasingly, right? Therefore, if it is pulled away the increasingly, your positive charge, your atom become more positive ion, charged ion. Therefore, you need the more energy to remove the electrons. It is closely bound with your nucleus. That is the reason why they are telling like that. Therefore, further, a sharp increase in the ionization energy occurs when an inner shell electron removed compared to the removal of the outer shell electron. We should be very careful about that. We already studied. When it is having the stable configuration, you have to provide the more energy to remove one electron from that. If it is loosely bound, just the valency electron, you need the less energy to remove it. This is what they are telling is why there is the sharp increase in the ionization energy. Yeah, when you are removing one electron from the inner shell, right? So therefore the ionization energy, you can see a sudden or sharp increase there. But compared to the removal of the outer shell electron, which is what the loosely bounded with your nucleus, therefore it shows distinctly low ionization energy. This is because, yes, why they are, what is the reason for this? The electrons in the inner shell, which is attacked very effective attraction. Why? The electron and the nucleus, which is too closer compared to your outer shell electron. That's why we are providing the more energy for that, right? The frequently the ionization energy is expressed in kilojoules per mole. That means by considering 1 mole of atom or ion. Right. Why this increasing? Yeah, if the attraction between the nucleus and the electron is high, means you have to provide the more energy. So when it is happens, it is attracted toward more strongly. That's why you can see the sharp increase in the when you are removing the electron from the inner shell compared to the outermost shell, right? So here we are going to explain the ionization energy in kilojoule per mole according to that mole of atom or and next we are going to speak about the periodic trims in the first ionization energy. So whenever we speak about the periodic trims, the mostly we are speaking along the group, along the period down the group. That is the specification. Right. The first ionization energy generally increases as we move across a period. Yes, I already said. So across the period, the left to right, always the ionization energy, the first ionization energy is increasing. So usually what they are telling is your alkali metal shows the lowest ionization energy when you compare with what the noble gases which able to show the highest ionization energy. I'll go through the rule why it's so, right? And next, generally the first ionization energy decreases down the group as we move top to bottom. The first ionization energy decreasing. What is the reason? That is also we will discuss. So this is one the example. When you take the group 1 element, Down the group order is given. Yeah, the lithium, sodium, potassium, rubidium, cesium, francium. Down the group, the ionization energy is decreasing. So actually, what is the reason for this? Well, the S and P block elements show larger range of the iron value than do the transition metal elements. That's why, guys, you can see in your periodic table there is a breakage between the transition metals. Why? Compare your transition metal, your S and P block showing the larger range of the ionization, first ionization energy than your metals. Generally, what is the reason? The ionization energy, even though within your transition metal, it slightly increased from left to right, like your periodic table. Actually, what is the factor? It's influencing your ionization energy. Simply same thing what you already studied, that the factor influence is the ionization energy. The first one is the atomic size. So what is happening? Down the group, the number of shell is increasing. So as the number of shell is increasing, the attraction between the nucleus and the valence electron will increase. Therefore, down the group, the number of shells increases now. The ionization energy is decreasing. And also, the energy needed to remove an electron from the outermost occupied shell depends on both effective nuclear charge and the distance of electron from the nucleus. This is what simply I said earlier. If you want to remove an electron, the successive removal of electron, it depends on the two things. The outermost electron, that is what you have to remove. Why? The two things, the one is the effective nuclear charge and the distance between the electron from the nucleus. Yes, if the distance increases, you can easily remove the electron. Therefore, you don't need to provide that much energy. Therefore, the energy is low, decreasing down the group. And down the group, what is happening? The number of shell, addition of the number of shell is increasing. As it is increasing, the nuclear charge, effective nuclear charge, becomes less. So therefore, down the group, what is happening? The ionization is decreasing. Along the group, why it's increasing? Yes, your nuclear charge effect is increasing. So therefore, what is happening? The attraction is increasing. You have to provide the more energy to remove one electron from your outermost shell. So that's why along the group the ionization is. This is what I already said. Either increasing the effective nuclear charge or the decreasing the distance from the nucleus increase the attraction between the electron and the nucleus. So this is the reason. The attraction increases, it becomes more difficult to remove an electron, and thus the ionization energy increases. Simply, they are telling us. If the effective nuclear charge increases, or the distance between the nucleus and the electron decreases, which increase the attraction between the electron and the nucleus. Thus the attraction increases, what will be happen? This is very more, the attraction increases, really it will become really difficult to remove the electron. Therefore, your ionization energy is increasing. Why? You have to provide the more energy to remove the one electron from the outermost section, which is very strongly attract together. So the trends in the first ionization energy in the periodic table. So I said, let's keep on your eyes. Along the group, the ionization energy is increasing. You can see your sp orbital, the alkaline earth metal is showing the less ionization energy than your noble gas, where the noble gas shows in the highest ionization energy. This is what the periodic table. What is the reason across the period, right? The nuclear effect is more. Therefore, the distance between the nucleus and the electron will become less. The attraction is high. You have to provide more energy. therefore the ionization energy is high. So the down the group, so yeah, the top down to top is increasing, top to down is decreasing. What is the reason? The number of shell, addition of the shell. Once it's happened, the distance between the nucleus and the electron become more. Therefore, the attraction, the nuclear charge, effective nuclear charge will become less. Therefore, the attraction also less. So down the group, you have to provide the less energy to remove the electron. Therefore, that's why down the group, what is happening? The ionization energy is decreasing. And why this break? I said, the in between you can see the transition metal. Compare your S and P block element. The transition metal shows the less ionization energy. That's why you can see this breakage, right? But within the transition metals, left to right, the ionization energy showing the slight increment, right? Next. So, acids. The variation of the first ionization energy with atomic number of elements. Guys, this is what we say. Always, your noble gases showing the highest ionization energy and your alkaline metal, right? Alkali metal showing the lowest ionization energy. You can see what is the reason. It is showing the stable configuration. Therefore, you have to provide the more energy. The stable configuration means what? It has the highest nuclear effect. Therefore, it is able to hold together very strongly. Therefore, you have to provide the maximum amount of the energy to remove an electron. So look at here, the outermost shell having only just a one electron, which easily you can remove. That's why the alkali metal having the least ionization energy compared to your noble gas, right? Okay. Anyhow, there is the irregularities in the trend of the first ionization energy when you given for such a period, but still you can readily explain this. So what is the reason I said the removal of electron from a completely filled shell? It could be 2, 12, 18, and half filled shell should be 7, 15, which are generally stable. Therefore, you need more energy. So that means to remove an electron. Therefore, the ionization energy also will become higher than is expected from other common fields. So you should be very careful about that. Why I am telling about the completely filled shell? So when you take the completely filled shell, you will have the 1:2, right? If you take this shell, yes, 1:2. You can say it's NS2, NP6. So this is the reason, as it is the stable configuration, right? So you have to provide the more energy to remove one electron. Therefore, the first ionization energy is equals. This is one, the full fill subshell. If you're having the half fill subshell, you will say 1s1, NP3, right? 3d5. This is having what? The half fill shell. That is also showing a somewhat higher stable compared to the other trade. So this what you have to provide the more energy to remove one electron for the stabilization. So the example, in the second period, the neon with completely filled shell has the highest first ionization energy. And look at your next one. The beryllium with complete S subshell shows the first ionization energy greater than the expected, and it even exceeds the ion of boron. So this is, you have to be very careful about that, right? When your S subshell, any subshell, it's completely filled or half filled, it will exceed the electron configuration, that is 7. Okay, 1s2, 2s2, 2, 3. I said it's 1, 3, 5, 3d5. So this is what the half-filled one. We are telling this is what the half-filled electron. Sorry, this is what the half-filled electron. This is also somewhat showing the stability. Therefore, it shows a little bit higher ionization energy. Right? The variation of the first ionization energy along with first and second. This is very important. Keep on your eyes. I'm going to explain this one by one. I need a red color. Right. And look at here. The hydrogen is 1. The helium is showing the highest ionization energy while the filled shell. Right. And again it's dropped down. And we are starting with, according to your period, it's starting with lithium. You are having the least one, that is 2s2. Again, the beryllium is showing what? 1s2, 2s2. So the filled subshell, again, that is what? Highest ionization energy. And you can see the beryllium along with the reset, along the period, right? Along the period, the I1 is increasing. This is what we talk, but not it true. Along the period, where what is happening, there is a irregulation, that what we said. The beryllium is having the filled subshell, therefore it shows little bit up, right? The ionization energy. Again, the boron getting down, right? The boron getting down. Again, from that it's increasing slightly, and nitrogen is half filled subshell, right? The nitrogen shows half filled subshell. So that is also will show a little bit higher ionization energy. Again, there is a drop. The oxygen showing the drop, right? So what is happening? According to that, again it start to increase. The neon is the full fill configuration, your noble gas, that is shows the highest ionization energy. When you take your second period, this is your first period, second period. First period, that is the increasing ionization energy according to your period left to right, that is no problem. But the second period, there is a zigzag variation. The lithium is less than the beryllium, but beryllium increase, but again the boron decrease. From the boron, again it started to increase. Again the nitrogen is half filled subshell. From that it's dropped down to the oxygen. So again it started to up to the neon. Why? That is the noble gas having the stable configuration. Right? So according to that, we have completed the ionization energy and the impact on the periodic trends, right? So according to that, you should able to understand what is mean by the ionization energy. First ionization energy, second ionization energy, and how it shows the variation according to your periodic trends along the period and down the group. Even though there is a irregularities, what is that? How you can identify that irregularities? Those are very important. This is very important for your final examination too. So go through that and have a nice day. See you with another presentation, guys. Until that, see you. Bye bye. Assalamualaikum warahmatullahi